I'd like to talk a little bit about setting up a cooling curve on my water cooler. It's a Corsair H80i V2 cooler system. But I really wanted to find a way of making the optimal cooling curve to meet a target constraint of temperature of the CPU. I've been doing a little bit of looking online for methods to find the optimal cooling curve for a computer. And I must admit, what I found online was a bit under par, and I thought I could do a little bit better myself on that. So I've been working on that over Christmas, and I thought I would just share the results of this with other people in this YouTube video in case it's of any value to anybody. So what we're looking at here actually is the optimized cooling curve. Just quickly look at what the results are here. So this red line here is the CPU temperature. So you can see I've greyed out this area here, which was a bit of a false start. So the CPU temperature starts out at about 30 degrees, and then it quickly jumps up to above 60 degrees, about 62 degrees here. That is because I'm now running, at this point, running a CPU stress test. So that's running the processor at 100%. Now here's the temperature of the liquid cooling medium, the thermocouple, in the CPU cooler system. And you can see that because the processor is running at full pelt, that slowly starts to increase in temperature until it gets to some plateau level here that you see. And that basically, that cooling curve on the water cooler basically holds that CPU at 62 degrees very steadily over that period of time, which is about just over an hour maybe. So there's no overshoot or undershoot, or it's very stable, and I've achieved that using this ramp in fan speed. You can see it ramps up very particularly over time, and then of course when I switch off the CPU stress test, then it slows down and goes back to the normal low speed at the end of the test. So question is, how do you get a curve like that? How do you find what the optimal curve looks like in the system? And that's what I'll talk to you about in a little bit more detail in the coming slides. So it's about optimizing the cooling profile. Now I've got these slides here that I'm going to jump into just to keep my thoughts organized. And I'll also jump onto the machine and show you a little bit on the screen what's happening there. So of course, there are lots of different motherboards and there are lots of different water coolers, but just to show you what I'm working with here, an Asus ROG Strix Z370 motherboard. Now, on this motherboard, we have a number of fan headers. There are a couple of headers here. There's a CPU fan header, and then a CPU opt, which is basically an ability to run two fans. There is a couple of spare headers here that can be used for one or two case fans. And there's also a header here for a water pump. So in principle, you can take a unit like this Corsair system here. So we have here a block for the CPU, lines to a radiator, and then the radiator, like in this picture here, is sandwiched between two fans. Now, those fans can be controlled either by plugging the fans directly into this header here, the CPU and the CPU opt, which are coupled together, so they always run at the same speed because they're designed for two fans that are sitting on one CPU cooler system. So that could be an air cooler or a liquid cooler. It doesn't know, and it doesn't care really. And then the other line here, this line on the cooler, can be plugged into the water pump header. So this motherboard in principle can control that. However, there is another way to control it, and that's to make use of plugging this plug here into the CPU header, which is useful if your motherboard needs to have that in order to boot. And then the fan control, these two fans can be controlled by plugging the fans into this unit here. So there's some circuitry built into this here, which can be linked into some other software through a USB line. I'll talk about that in a few minutes. But the beauty of the motherboard connections is, as far as I was aware, was that we could use a utility such as the Asus Fan Expert to be able to control and optimize cooling curves. So I'll just show you what that looks like. So it's a piece of software, and you can look this up online. But I mean, basically, it can control the case fans, it can control two CPU fans, it can control a water pump. The curves can be customizable. That's good. one of the things is, because you can't link it into the water temperature, because it doesn't read the water temperature, it's looking at the CPU temperature. Now that means that when the CPU ramps up in heat, if you suddenly go up to a high CPU usage, the system responds very quickly and you get a pulse of high fan speed. Now it's possible to adjust the spin up time of the fans down here. So for example, there is a screen to do that. But I actually found that I mean, there must be some safety mechanism that's built into the software that overrides this. So my experience with this software was, irrespective of the fact that you were using a water-cooled system and it knew you had a water pump system, it still looked at the processor temperature and the processor utilization, I think. And then when it saw a sudden leap in temperature going up, it would increase the speed of the fan. And that meant that I would get a pulse of noise from the computer. And that's really not what I want at all. And I couldn't see any way to sort that out. So in fact, actually, what I think is better is the Corsair IQ suite. There are various different profiles here. You can have quiet or balanced or extreme or even custom curves. And the custom curves are really useful, and we'll make use of that in the development of an optimization. And also another nice thing about this software suite is there's data logging possibilities. I'm just going to quickly go to that software now and take a look at that. So this is my software here. It's running custom 1. This is the custom curve. That curve is the curve that's used to achieve the graph that I showed right at the start. But one of the nice things about this is that you can set up another curve, another custom curve. So let's change that now to custom 2. And if we look at the fan speed now, it's running at about 1140. Actually, it's increased a bit because this is a new curve. But now we can just change this now and set that so we can run the fan at full speed. So here it is, running at 2,600 RPM. That's now us in control of the fan, taking manual control of it. And that's all well. That's great, because I can use that now to change the fan speed to different levels, and then run the fan now at, say, that's I think 46%. So 46% of the maximum speed will now converge down onto a new value here, and it looks like about 1,500 R. Well, I don't know. We'd need to take an average on that figure, but anyway, you can adjust the percentage of the fan speed as a function of maximum, so 100% down to 25%, and that's the beauty of this custom system. So I'm just going to put this back onto custom 1, which is my custom cooling curve. The other point is here, you can choose various things to measure and to control the temperature. So you can look at, for example, the package of the core, or one core in particular. You can look at why you would want to, but you can look at the temperature recording of the graphics card, or you can look at various temperature points off the motherboard. But I think what we're really interested in here is the actual coolant temperature, and that's the coolant that's running around inside the radiator and inside this. And that, of course, responds much more slowly. That temperature changes much more slowly as a function of what's going on in the machine. Another nice thing about the software is that you can do sensor logging. So you can select various different measuring points off the motherboard and off the cooler, the HATI cooler system, and then you can then store that to a file and start logging and build up data. So very nice. And just another thing is you can also take a look at various things that are going on the motherboard, but that's not directly of interest to us now. So just going back here. So I've talked a little bit about that software suite, the fact that we've got data logging possibilities, and that allows us to do some experiments with how the system will perform with various different fan speeds as a function of running the processor at maximum load. So, okay, here's a little thing that I wanted to point out. You specify the percentage of maximum fan speed. So we can measure what the RPMs on the fan are, but we don't measure the percentages. So we need to build a correlation between the percentages that we put in, like 100% or 50% or 40%, and what the actual speed of the fan is in terms of RPM. So this is a graph of that. So this is the fan speed, so 500 RPM, 1000, 1500, 2000. And then this is the percentage that correlates to. So 100% is, well, I don't know, whatever, it's just something over 2,500. I'll give you the exact figure, perhaps a little bit later. What I was expecting, and I was a little bit surprised about this, was when I actually plotted that out, and I used the average value. So when I was running it at a particular regime, say 100%, 70% and 40%, I think were the figures that I used, I've measured all of this data, and there's a lot of it, for the fans, and used the average value. So we've managed to get a sort of fairly noise-free data point for what the RPM are at various percentages. And in fact, actually, it's not a completely straight line, which was a bit of a surprise to me. So there's a kink in there. Yeah, okay. So I've just fitted a straight line to it, and that's the equation for the straight line. So actually, one of the things that I just wanted to quickly talk about is the data file that comes out. So when you actually run the logging, you get this kind of data, and you can see here the various headings, and you can see here that the numbers are written down. Each one of them's got RPM or degrees C here, which of course is not what you want from an Excel perspective. We need to turn these data into numbers. So I'll just do Control C to copy that into the buffer, and then I'll do Control H as a replace, Control V, so I'm paste that degrees C symbol, and then I'm going to replace all. So 214 replacements are made, and you can see that I've got rid of that degrees C from those temperature measurements there. You can do that if I do Control H and then replace all of those. We've made a whole bunch of replacements, and we've now converted all those RPM figures, all of those rates into pure numbers as well, which we can manipulate. In the same way, we need to convert the date and then replace all of those, and then you lose part of the date flag, and then we have to do the same with the PM. If we do that, Control H space PM and then replace all, then we have these actual units of time here. And of course now we can convert that into time in seconds or minutes or hours or whatever one wanted to do. But those are, so now we have a sheet that is manipulatable in Excel, and I'll come back to that. Oh, and also I will put a link into the spreadsheet for all the calculations that I've done here. So if anybody wants to, just to look through the work that I've done. So for example, these are the measurements for the that I used in the model building exercise. And this spreadsheet with the various models and the various calculations and graphs, I'll supply that as a link. So here's the data collection exercise. So now we can control the fan at different speeds. So let's start off with the fan at 100%, so that's full speed. So basically, cooling, the way it's working is we've got the ambient temperature, which was in my case about 19-20 degrees. Then we've got the temperature of the water that it eventually gets to at equilibrium condition, and then we have the temperature of CPU at equilibrium. And if you run the system for a long time, then you will get these values under a constant ambient temperature condition. So what we see happening is we've got this purple bar here. This is the CPU load. So you can see that I've gone from a CPU of very, very low load, so a few percentage points. Then it jumps up to a high level of load for about an hour and then drops down. And what you see happen there, this red line here, is the CPU temperature. It goes from about less than 30 degrees on average. It jumps up to just below 60 degrees and then converges at about 60 degrees. And then we switch the load off the CPU. Then that CPU temperature drops. And what you see here happening to the water temperature in the cooler system is it tends to this value here, about 30 degrees in this case. So I've let the system cool down and equilibrate a bit. And now I've redone this exercise here, now using the fan at 70% of the maximum speed. So now we switch the processor on at 100% by using one of these burn-in pieces of software, and the temperature again converges to a figure now a little bit above 60 degrees here in this case, 60 something, 62 degrees or whatever it is. That's where it tends to sit. And in fact you see that the water temperature actually is a little bit higher as well. And I would say that the water difference between that water temperature here and here is greater than the difference between that and that, very slightly. Okay, so repeat the experiment now. do it now with 40% of the maximum fan speed. So the cooling is a lot lower now in this case. So processor up to 100%, the processor increases in temperature and then comes to a sort of more or less stable value, and the water temperature in the cooler heats up now to somewhat more significantly higher temperature, and it may not even have converged yet. I think it may have a little bit of climb left in that. I mean, that's an interesting curve, that is. You can fit a curve to that using Newton's law of cooling, and so one can calculate what, using that curve, one could calculate what that endpoint is. But I did think I was going to have to do that, but yeah, it's not important. So now we have enough information to build a model. So what I've got here is the fan speed in revs per minute obtained from the file against the CPU temperature and the Corsair H8Ti V2 cooler. So you can see here's the CPU temperature, and it's not a straight line, it's a little kink, it's a little curve, and that really is capturing the fact that this difference here is not exactly linear. You see, it's moving. So there's a bit of a difference here and a bit more of a difference here. And then if we use that equation, you can then plot the same thing out here, but in a more continuous fashion, extending a little bit beyond the range of the actual experiment. And the beauty of this is, I mean, it's a reasonably good model for something like this using a logarithmic function. Well, okay, so what have we got? Right, in summary, we've got some water temperatures that we can think about. What are those water temperatures? What are those water temperatures that we might be interested in setting? What does that translate into the maximum CPU temperature? How fast does the fan need to go in that? And then ultimately using that correlation, what percentage of this fan speed that is? Well, using the relationships that we've just seen, so they're interrelated. I guess the way to look at it logically is at that fan speed, you would end up with a water temperature of 32 degrees, and then you would end up with a maximum CPU temperature of 61.6 according to this. We can then also use those fan speeds to calculate what percentage that would be of the maximum fan speed. What do we want to run the processor at? Well, when I was doing these experiments, the room temperature, as I mentioned earlier, was about 20 degrees, 19, 20 degrees. So we want some headroom in the picture. We want some headroom in case there's a heat wave, and you could easily see the temperature going up certainly 5-7 degrees in the summer on a hot spell from that. Well, that would push the CPU temperature up to about 70 degrees. Say if we were choosing this red region as our benchmark. There's also other factors such as, for example, the graphics card. One could be running the graphics card very hard as well at the same time as the processor under certain conditions. And we don't want the machine to overheat, so we want some headroom. So this is why you see we've chosen here a figure of 61% of maximum fan speed, equating to an RPM of about 1678 RPM, with an expectation of a cooling water temperature of about 34 degrees. Under 100% load, that would achieve a CPU temperature of about 63.1 degrees. So that's a reasonable sort of limit that we might want to base our model around, with some potential headroom, of course, because we can increase the fan speed quite significantly beyond 1678 to about 2500. So there's still quite a lot of additional cooling capacity if, for example, there was a lot of heat from the graphics card, and if, for example, there was a lot of extra ambient heat from hot weather. If we set 61% as our figure, given the fact that this is sort of a 2 degree increment here, all what we need to do is sort of invert this relationship, which is basically writing these percentages down in the opposite order. So that's what I've done here, flip them around. So here we have 61% should be our maximum fan speed that we would be likely to achieve in order to keep the temperature at about 63 degrees on the CPU under conditions such as there are today or around now, which is a room temperature of about 20 degrees. And in the event that it was a few degrees hotter, then there's plenty of additional fan capacity, another 40 40% of capacity that we can deploy in order to keep the CPU under control. So, using that relationship here of fan rates, we've programmed that curve in, and you can see this is the response. We see as the processor produces heat, and throughout that whole process, because that cooling curve is matched to the system, we see that there's no overshoot on temperature or undershoot. It's very well tuned, and just the CPU temperature just reaches the threshold, a steady threshold throughout that whole process. And of course, under times where you're running the processor at less than 100% utilization, your fan speed will of course be significantly lower than 61% of the maximum utilization. Now, of course, like I was saying previously, in the event that we have adverse conditions such as high ambient temperature, or we're using a lot of additional processing capability in the computer by a lot of data transfers, as well as a lot of graphics processing generating a lot of heat, there's still a great deal of cooling capacity left. So I think that's pretty nice result. As I mentioned before, in the comments I shall put links to this Excel file and the PowerPoint presentation. I hope this has been useful for anybody who is interested in doing something similar. Thanks. Bye-bye.